Hello, this is Dr. Orlando Lignami. I'm starting here our live sound and sound in studio course, and this will be a very interesting and intense course because we will cover many concepts of the Tonmeister, which is the most important program in audio production in the world, the Tonmeister concept in Europe. And I'm going to be using a book that you have in the syllabus that it's out of print. So you have a lot of information in these presentations, but you probably won't be able to get the book because if you find it, it's very expensive. So I recommended another one that you should get anyway. The Bobby Olsinski book, and his books actually are great. So you can buy all of them because they are all very good. In this slide, you can see the sound waves, and the sound waves, the way we have to think of is like spherical waves. They are not even circular, as you will see. It's three-dimensional, so they go in all of the directions. But when you go very far away, they become parallel, as you see in there. This is going to affect a lot how we do our job as sound engineers and mixing and mastering engineers. You already know the relationship between the frequency and the wavelengths. We can see here in this graph as well. In the ruler in the middle of the page, you can see the relationship between the sound pressure level in dB and the sound pressure level in the normal newtons per square meter or pascals as the physical measurement is. As you know, the speed of sound is about 330 meters per second, which is extremely fast, of course, comparing to the regular speeds that we are used to in our regular life, in our everyday life. And you can see that in this graph in letter D in there, the distance that the sound travels or propagates in time. So in 2 milliseconds, we can see that zero point 0.7 meters is the distance that the sound travels, which is quite a lot in only 2 milliseconds. In 30 milliseconds, which is something that we can already perceive, the sound can travel about 10 meters. So of course we can see this difference when you have very large distances, but the small distances as we have in the studio, they are very small. They are not as noticeable as in large distances, but they will affect also many things that we do here. In E, you can see the relationship between the size, the wavelengths, and the frequencies. And you can see from this scoring there, the lowest frequencies that we can have about 33 hertz all the way in the bottom of the piano. They can go about 10 meters. And all the way up in the piano, we have 0.08 meters, which is a very short wavelength. Here we see a very important concept, which is the relationship between the obstacles and the wavelengths. And the obstacle that you can see in there is the head of the person, of the listener, which is extremely important for us. So when we have a very low frequency, we have a very high wavelength, right? So for example, the 130 hertz in there on the right, the size, the length of the wavelength, it's larger than the obstacle. So it passes through right, through our head or whatever obstacle that is, it is, more or less in the dimensions of our head. But when we have short wavelengths, like in higher frequencies on the left, we see that there is a shadow on the side, so we can perceive actually better the localization of the higher frequencies rather than the localization of the low frequencies because of this particular reason. To discuss the room acoustics, we need to understand also that the sound can be reflected, as you can see in there in this particular picture. We'll discuss this more later, or it can be absorbed by a certain barrier. Here we have extremely important concepts. You see that when we have a sound source and a listener in a room, There is a sound that is called the direct sound, which comes directly from the source to the listener. Then we have what we call the early reflections or first reflections, when they only bounce once. You can see that in these lines that go in the room, they have different thickness. That is the amplitude. So the direct sound is the loudest one. Then the early reflections or first reflections start to be a little softer already because the sound loses energy, right? And then there is a build-up of the reverberation, which happens later in time, and that becomes softer and softer. So this is extremely important to understand, that we have the sound level, the loudest is the direct sound, the early reflections, and then the reverberation build up. This is going to be extremely important for us to be able to do miking, correct miking, and also to use the reverb units that have those controls that you can see in there. Here we see that we have a very interesting localization of the direct sound. We know exactly where the sound source is. The early reflections we don't notice very well, but when we do, we can see where they are coming from. But the reverberation comes from everywhere. Another very important concept is the relationship between the sound level of the direct sound and the diffuse sound, which is the reverberation. We will talk about this a little more later, but you can see that the diffuse sound is more or less the same all the time if you are in the room, and the sound level decreases. Depending on the distance and the time, the distance from the sound source. Here we see a relationship between the shape of the sound sources and the sound level according to the distance. This is very interesting. We have three different sound sources here. One is a point sound source, which is a very small one. A line sound source, which is something that is in a line. Which it's not very common, but we can think of something at a distance. For example, a train running, downhill. You see a train, all the way down there. And the plane sound source is something that has a lot of dimensions, in all directions, such as a big instrument like a piano. So you can see that in line number one in there, the point sound source, the intensity, the sound level decreases 6 dB every time we double the distance. Pay attention to this. We double the distance, the sound level decreases 6 dB, and I can tell you that this means that the intensity is half of what we heard before. So if you are at a certain distance from an instrument, a point sound source, and you double this distance, you will decrease 6 dB the intensity, and we will hear as if it's half as loud. This does not happen with the line sound source, because instead of being a spheric, a sphere, the sound waves, they will be like a cylinder, and this means that the will decrease a little less. It won't decrease as much as in the point sound source. That's why we hear, for example, a train, as I said, from a very large distance. When we have a more complex shape, like the piano, we have a different situation here. The sound level decreases not as much when we just double the sound source, and it starts decreasing more and more when we go to larger distances. So this completely changes the way we look at the sound sources. When you are miking something, you have to be aware of this, because you know how much of the direct sound you get depending on the distance that you're going to put this microphone. Here we see again the shadow effect and also a graph with the estimation of the diffraction effect of obstacles. So this is the size of the obstacles, the obstacle in meters, from a very small one to all the way to 30 meters, and the frequency in the bottom. Here we see some interesting relationships between the shape of the reflecting barrier and also the extent. So you see that if the sound barrier is very small, we have a particular effect on higher frequencies, but we only have effect in lower frequencies if this is very large. So this is the graph that you see on the right. We only perceive the sound reflections if they arrive at about more than 50 milliseconds. Less than that's very difficult. And the first reflections together with the reverberation provide a significant sound clue to the room's interior. The size, proportions, and treatment, the listener's surroundings, and all of that. And this table explains more or less of this certain situations where we have the sound reflections making a difference on if in its effects on listening, recording, or both. We call sound coloration some problems that we actually have inside certain rooms. So, for example, when we have early reflections that bounce very quickly, the number here actually is between 1 and 15 milliseconds. Usually, those are room or floor reflections. They can cause an effect called comb filter that you can see in picture E, figure E. And also, if you have two standing, two parallel walls, this can cause an effect that is known in physics as standing waves and flutter effect. And we hear this as an echo that repeats very quickly several times, and this is called fluttering, and it's a very bad effect, sound coloration in a room. The absorption that we have depends on the type of material that the barrier is made of. So we can see here two types. In the top, the high frequency absorbers that we have two examples, and the absorption coefficient. This little graph in there, and you can see on the far right, the reverberation time, how it decays with the frequency. And the ones in the bottom are the mid-range absorbers, and you also have the reverberation time on the right, which means that we have less reverberation in the mid-range in those cases. Here we see examples of low-frequency absorbers or bass traps, the ones that will absorb the low frequencies. This graph shows us the different kinds of absorption coefficients of ceilings and walls and their relationship to the frequency.